Hey, have you ever punched an inverse trig function into your calculator and just kind of stared at the answer, wondering why it gives you that one specific number? Well, you're in the right place. Today, we're going to tear into inverse trig functions, and I promise by the end of this, all those confusing rules are actually going to make perfect sense. We're going to unlock the why behind it all.
So let's kick things off with a little puzzle. We all know that the sine of 30 degrees is 0.5. No big deal. But wait, the sine of 150 degrees is also 0.5. And if you keep going around the circle, the sine of 390 degrees is 0.52. There are infinite answers. So why is it that when you ask your calculator for the inverse sine of 0.5, it only ever gives you one answer, 30 degrees? Where did all the other options go? Well, understanding that one single answer is the key to our whole story today.
To solve that calculator mystery, we've got to rewind a bit. The real issue isn't with the inverse function itself. The problem is actually with the original function, like sine or cosine. This is what we call the inversion problem, and it's the reason you can't just take a sine wave, flip it on its side, and call it a day.
And here's the absolute heart of the issue. Trig functions are what's known as many-to-one. It's a fancy term for a really simple idea. You can have many different inputs that all lead to the exact same output.
Let's just use sine as our example. The sine of 0 degrees is 0, okay? But the sine of 180 degrees is also 0. And, you guessed it, the sine of 360 degrees is 0 too. See? We have three totally different inputs, all pointing to the exact same output. Now, imagine you're the inverse function. If I come to you and say, hey, the answer is 0, what was the question? You'd have to shrug and say, I don't know. Was it 0, 180, 360, or maybe minus 180? There's no way to give one single confident answer.
And that is the fundamental deal breaker. That's why a many-to-one function isn't technically invertible. It fails the most basic test. To have a real, true inverse, every single output has to trace back to one and only one input. So, if they're not invertible, how in the world do we have entire chapters in our textbooks about them? Well, this is where mathematicians got really, really clever.
The solution, and it's a brilliant one, is all about restriction. It's about taking that infinitely repeating, messy wave and drawing some clear borders on it to make it useful and predictable.
And this brings us to the hero of our story, the principal value branch. That's the official name for this specific, agreed-upon slice of the function that we're all going to use. By basically chopping off all the repeating parts, we force the function to behave. We make it one-to-one inside those borders, which means every output now has exactly one input. Problem solved.
You know, the best way to think about this is like making a map. The full sine function is like a globe. It keeps spinning and repeating forever. If you try to flatten that whole globe onto a single sheet of paper, it would be a distorted, unusable mess, right? So what does a map maker do? They choose a section, they draw clear borders around it, and they say, okay, everyone, this is the map we will all use. The principal value branch is just the official world map for that function.
So here's the process in a nutshell. First, we restrict the domain. We draw our map's borders. For the sine function, we've all agreed to only look at the section between negative 90 and positive 90 degrees, or negative pi over 2 to pi over 2. Inside that little window, the function is perfect. It's one-to-one. And now we can invert it. And when we do that, something really cool happens. The roles flip. The old domain we just defined becomes the new range, and the old range becomes the new domain.
Okay, so this is where it gets super practical. Because mathematicians had to draw different borders for the different trig functions, we ended up with two very distinct groups. You can almost think of them as two families of inverse functions, and each family plays by its own set of rules.
This table lays it all out beautifully. So, meet the families. In family A, we have inverse sine, tangent, and cosecant. I like to call them the mirror family. Their range is centered right at 0, from negative pi over 2 to positive pi over 2. And when you give them a negative input, they do something simple. They just mirror it by popping the negative sign out front. Then you have family B, the detour family. This is inverse cosine, secant, and cotangent. Their map stays up in the positive values, from 0 to pi. And because of this, when they get a negative input, they have to take a little detour. The answer is pi minus the result you'd get for the positive input.
Now, I know that sounds like a bunch of abstract rules. So let's stop talking theory and actually put it to the test. A good old-fashioned side-by-side comparison is the best way to see what's really going on.
Here's our challenge. We're going to solve for the inverse of negative 1/2. We'll do it once using a member of the mirror family, inverse sine, and then we'll do it again with a member of the detour family,
inverse cosine. It's the same input, but two different families. Let's see what happens. First up, family A. We have the inverse sine of -1/2. Okay, it's a mirror function, so the rule is super straightforward. That negative sign just gets to pop right out front. So our problem becomes negative inverse sine of +1/2. We all know the inverse sine of 1/2 is pi/6, so our final answer is just negative pi/6. Simple as that.
All right, now for family B, we've got the inverse cosine of -1/2. Now remember, this is a detour function. We can't just pull the negative out front, no way. We have to use its special rule, which is pi minus the inverse of the positive version. So it becomes pi minus the inverse cosine of 1/2. We know the inverse cosine of 1/2 is pi/3, so we just do the math. Pi minus pi/3 gives us a final answer of 2 pi/3.
Now hold on, let's just look at that. For the exact same input, -1/2, we got two completely different answers. For inverse sine, we got negative pi/6, an angle down in the fourth quadrant. For inverse cosine, we got 2 pi/3, an angle up in the second quadrant. This is proof positive. Knowing which family a function belongs to is everything.
So let's bring this all home. Let's do a final summary to really lock in why these borders, these principal value branches, are so incredibly important.
Honestly, this table right here is the ultimate cheat sheet. Just look at the two family leaders, inverse sine and inverse cosine. Their domains are exactly the same, right? You can only plug in numbers from -1 to 1, but their ranges, their maps, are totally different. Inverse sine lives in quadrants I and IV. Inverse cosine lives in quadrants I and II. And that single difference, the location of their map, is precisely what causes them to have completely different rules for handling negative numbers. So, the main thing to take away from all of this is that the principal value branch isn't just some random, arbitrary rule that was made up to make your life harder. It's the exact opposite. It's the clever, elegant solution. It's the border on the map that takes a function that's impossible to work with and makes it predictable, reliable, and useful. It's what makes the entire journey possible in the first place.
And that leaves me with one final thought for you. We just uncovered the logical, clever reason behind a rule that for most people feels totally random. So it kind of makes you wonder, doesn't it? How many other arbitrary rules, in math or in any other subject, are just like this one, a brilliant solution to a hidden problem, just waiting for us to understand the why.